All right, happy Tuesday. How's everyone doing? You might be busy at this time. It's that time of the year. It's also really nice outside. It almost feels like a shame to be inside. As economists, we talk about opportunity cost. The opportunity cost of being inside is so high today. So let's see. We're through almost all of the material in this class. We have part 5 to cover, which we're going to start in class after the mini exam on Thursday. This is a more complicated extension of the tools we already know. So in a lot of ways, part 5 is not going to be, it doesn't do a whole lot of like conceptual extra lifting. But that's really where the big model that we use in the field you can see in its full detail. So part 5 is a big deal, but most of the groundwork has already been laid at this point for what we're doing. A couple of housekeeping things. I posted homework 4.3 and 4.4. I'm automatically giving everyone an extension on this. I think extra time at this point in this semester is probably just a good thing. So take that if you wish. If you want to give yourself the 5 p.m. deadline on Friday, feel free to do that. It's not posted to Canvas yet, but it's on the course page. So those are the 2 homeworks. What we're doing today is a bit of review. So I've posted the mini exam 4 demo to the course page. This looks very similar to what you can expect on the mini exam. I recorded this last semester. There's a small chance I'll update it for this semester, but it's very similar to what we covered last semester. Bless you. What we're doing today is covering some extra questions I just wrote up as a bit of extra review that we can do in class today. So we're going to do that at the beginning of class. And then the back half of class, we're going to break out and talk about the part 4 project. So we skipped the part 3 project. It's sort of challenging to do a part 3 project. So we skipped it. We're doing a part 4 project, which you can simply use the data sets you used for the part 2 project. The main extension is just building a statistical model on top of that data. Like the earlier part projects, you can work in a group. I recommend you work in groups of 2 and 3. If you want to work by yourself for the final project, just let's sit down and have a conversation about it. There's a reason I like people working in groups, and that's mostly for managing the workload. I don't ban working by yourself. A lot of you would prefer to work by yourself. We just need to have a conversation about it just to make sure you're up to speed on all the tools that are required for that. Does that sound nice? Okay, I'll take that as a yes. So that's where we're going today. We're going to spend the first part talking about mini exam review, and then the second half breaking out. You can chat with the people around you, maybe find groups if you don't already have them, and then we can also troubleshoot some coding as it's coming up. Okay, and then on Friday we're going to hold a part 4 project workshop. So we're just going to have the department open. You can drop in for questions about your part 4 project. This is really where the final project starts coming into focus. So just keep that on your radar. This is not something to just breeze through and submit. Be thinking about the final project as you put this together. Okay, so y'all want to do some work? So I brought some questions. This is not a lecture. We'll talk through these ideas, but I'm expecting you to put in some work with these questions. So let's just get this started. This was Maxine over the weekend. It was so nice. We came into Oakland. Let's see, when was that? Was that Saturday? Saturday wasn't as nice, but we came in, went to the La Gourmandine, and then Red Hawk Coffee, right next to each other. So Maxine just sitting in the window, and then right afterwards we went to Phipps Conservatory. So that was, it's like about as perfect a Saturday as it gets. Yeah.
When is the chapter 4 homework due?
That'll be due on Sunday. I'm just giving everyone an extension on that. So Sunday night. Yeah.
Okay, so it still says due on the 29th, so are you gonna put that in?
On the 29th, on the course page.
On the grade scope.
Let's see, grade scope. Oh, for this homework, you mean?
Yeah.
So that's is that the?
Was that last homework?
That was the last homework. Yeah, that was the one that was due over the weekend.
Okay.
Yeah. Yeah, good. Any other housekeeping? Yeah. Yeah. They should be back to you pretty soon. That's like top of my list. Yep. What else? Any other? Oh, mini exam 3 should be back to you today. So it'll be back this evening. Any other questions? And I think the grader is getting the homework back to you in the next couple of days. He said he's been a little bit behind on that, so apologies from us. Any other questions? All right, well, I have questions for you. So we're going to hop over, and I'm going to put some questions on the screen. We're going to break out into groups. We can sort of treat this as a pseudo review session. So these questions are for you to work through, and then we'll put the answers on the screen and talk through how things are going. And we can take all the time we need for this. I have the entire class period devoted to this. If we end early, that's when we'll start talking about the Part 4 projects, which I expect we will have plenty of time for. But we can take all the time we need. Okay, so this is just an outline of what we've done. We've talked about predictor variables, so how we build a relationship between x and y using linear models. In part 4.2, we introduced the possibility of categorical predictors. So this was x not as a continuous numerical variable, but as a binary predictor variable, which is a binary categorical variable. So x would take 0 or 1, but the model itself was identical. So everything about this is identical. It's just a difference of the x variable. In part 4.3, we talked about model assumptions. So thinking about the linearity assumption. So we need the data to be linear. Homoscedasticity. So we need the variability to be the same at every point on the domain. Independence. So we needed the data points to not impact each other. And then normality. So this is like the normal distribution of errors, which we said doesn't strictly need to happen if we have a large enough sample size. And then in part 4.4, last class, we talked about time series and primarily the problem of it violating independence. So clearly, time series, the data points are very related to each other through time. So we talked about different ways of seeing this, what we call autocorrelation, and then some ways of handling this problem of autocorrelation using first differences. You'll see some of this on your homework, which will feel very similar to the exercise we ran in class. A little gift to you just to make it a little bit less work on your end. Okay, so let's think about the mini exam 4. So I have, I think it's 6 or 7 questions with a couple of different parts, and we're just going to walk through as many of these as we want to. Sound fun? The way this works as a quasi-review session in class. You're going to work on your own, try thinking these problems through. My goal with this is that you figure out what concepts you're struggling with and to identify what those gaps are. This is a great place to be able to do that. Don't try to get everything, don't try to simply give the answers. Think through what you don't understand and how you can go about fixing that problem. Okay, so here's a data set. I have two variables, the number of parks and the crime rate. So this is sort of like a part two kind of question. How would you visualize a relationship between these two variables? So we'll take a little moment here. Maybe say hi to someone next to you. This is going to be collaborative, like you can learn from the people around you. If you have questions, someone else probably has the same question, but if you have questions, someone else probably also knows the answer. So let's take maybe 2 minutes here. We'll get started, say hello, tell someone what you did when it was 75 degrees outside, and then maybe try thinking through this problem. Okay. We ready to answer this question? Some people have barely started, so. So how do we visualize this? Is that were you volunteering, Mairead? Scatterplot, nice, okay. Looks good. Is that what you're going to say, Anthony? Nice. Okay, scatterplot, nice. I would put this in the S tier of visualization tools. Definitely my favorite one. Okay, so write down a model to test whether more parks means lower crime. This is written in sort of causal language, but this we're not able to establish causality, so one way we could rewrite this is just saying, write down a model to test whether neighborhoods with more parks have lower crime.
specific notebook for this, right?
There's no notebook for this. Yep. Okay. Someone want to tell me an equation? Yeah, Pete.
Prime rate equals beta 0 plus beta 1 times the number of parts plus an epsilon.
Okay. Anyone disagree with this? We're trying to get a relationship between these two variables. This is a really nice model. I would probably put the crime rate as the variable we're trying to predict, which is our y variable like this. And then we're trying to use parks as the predictor variable. So this is how I would set up this problem. Yeah, very nice. Any questions here? And we can pause and go into as much detail on any of this as we think is needed. Okay. This is a nice picture. This is a low quality. This is not a low quality figure, but it's not of like top tier quality. Which parts of the model would indicate that a relationship existed? So this is just a picture of the data, and then I've plotted some coefficient values. What part of this of the model would indicate that a relationship existed? You can either use the numbers I have, or use the equation that you set up. Take about a minute here, and check with your neighbor if you want. Okay, someone want to give me a nice little answer? Anthony.
It's beta 1 because that's the slope.
So beta 1 is our slope coefficient. It tells us whether the slope, which is the relationship, is 0. So yeah, beta 1 would indicate to us whether a relationship exists, or whether a relationship exists in our data. Okay, any questions? Nice, all right. And then we'll come back to p-values in a little bit, but this would tell us under the null hypothesis whether a relationship exists. What about this one? So this is practice number 2. Now we have a binary predictor. So instead of the number of parks, I have a column called hasPark. Here, this is just 0. You can ignore this column. This is either 0 or 1. So if there's a park, then I've coded it as 1, and for all of the other areas, I've coded it as 0. So these neighborhoods have no parks, so we're saying it's 0. But there are some columns or some rows that do have some parks, and we're just calling those 1. In this case, using has park, we're going to set up a model. So the first thing to do is figure out what type of variable has park is. Let's take like 30 seconds here. This is one of those part 1 topics. I guess I sort of gave you the answer. Binary categorical, anyone? It's 0 or 1, and the 0 and 1 don't represent counts. They represent categories. So nice. What about this one? Visualize the relationship between has park and crime rate. So we'll take maybe a minute or 2 for this.
Is this slideshow gonna be on the website?
I can post it if that would be helpful. Okay, what do y'all think? Is that enough time? So yeah, so we could use, if we had 2 numerical variables, we could use a scatter plot, and then we could color them differently if we had a binary categorical variable like this. But we only have one variable, one numerical variable. What's maybe another idea? What about like a multi-strip plot? What about something like this? So I'm going to set up a strip plot. A box plot could also work. We just want the 2 categories on the horizontal axis, and then we have our numerical variable on the vertical axis. Any questions here? Okay, so next thing to do is to write down a model. I've given you a visualization of what the model could look like, but your job is to actually write this model down, and then interpret what beta 0 represents and what beta 1 represents. We'll take maybe 2 minutes here. This is like a sort of a 3-part question. I've done one of the parts for you, which is to visualize the model, but then your job is to write down the model that we visualized and then interpret the coefficients. Okay, someone want to tell me a model? Well, no model it is. So let me give you a model. I want to predict crime rate using whether we have a park. So this is just, I mean, it's essentially going to be the same model as this. So crime rate, beta 0 plus beta 1 times has park plus an epsilon. So this just gives us, the horizontal axis is our predictor, and then the vertical axis is our outcome variable. Yeah, he says.
Why isn't beta zero in the why is it just zero?
Yeah, so it's giving us, so we can sort of think about this visually. It's giving us the vertical intercept at the 0 on the horizontal axis. So that's like, it's hitting the middle of the data when the data is at 0. And the way we interpret that is just the average of the 0 group. Does that work? Okay. Any other questions here? Okay, so we interpret beta 0 as the average for the 0 group. This is always how we interpret the beta zeros. It's the average at 0. In this case, because we've coded one of the groups as being 0, then it tells us the average for that 0 group. What about beta 1? Well, this is just the difference in the crime rate. So this is like, we have two groups. We get a slope. The beta 1 just tells us what happens when we move by 1 unit on the horizontal axis. And because of the way we've coded this, moving 1 unit on the horizontal axis is just the difference between the two groups on the horizontal axis. So the beta 1 just tells us the average difference between the two groups. Okay, any questions here? So then to get the average for the parks group, so the group that has a park, we would just take the average for the 0 group and add in the average for add in the slope. So this is like we're plugging in 1 into our equation. So we just take this equation, plug in 1, and it tells us the average crime rate in the 1 group. Okay, any questions here? Essentially just using our model to make predictions. All right, what about this one? Instead of coding no park as 1 and park as, this is a weirdly worded question. So no park is 1 and 0 for park. How would our model change? So we're sort of changing the way we've coded this. How would we set this up? Let's take maybe 2 minutes here. So all we're doing is switching the framing from whether it has a park, we code it as 1, to if it doesn't have a park, then we code it as 1. All right, what do you think? Yeah, Pete?
The definitions of beta 0 and beta 1 is essentially like flip.
Okay.
So beta 0 is now the mean crime rate for places that do have a park,
Yeah.
and then the beta 1 is a difference between that to the ones that do not have a park.
Yeah. So yeah, beta 1 would tell us what happens when we go from parks to no parks. Yeah. Yeah, nice. So I think this is almost exactly what Pete was saying. Beta 0, instead of, in the previous model, we coded the 0 group as being no parks. In this case, we're coding 0 as being parks. So this is just the average for those with parks. And then here, this is just, it's the same magnitude, it's just negative. Okay. The point here is beta 0 is always going to be the mean of the group coded as 0. And then beta 1 is always just the difference between the two groups. And this is exactly the same kind of interpretation as when we have a numerical predictor variable. Beta 1 just gives us the slope. Beta 0 gives us the average at 0. All right, so let's do some reading. Y'all like reading? This is not fiction, so maybe less fun. Although I made this data up, so maybe we could call this fiction. Tough crowd today, all right. At least I try. So maybe that's a negative, I don't know. So this is our model. We have test score. We're trying to predict test score using hours of sleep. And then I just have a regression output for you. So we have 150 students, and then we're just trying to run a prediction model. So first thing to do is to interpret the intercept, which in this case is roughly 42. So let's take maybe 30 seconds. Interpret what this beta is telling us. Is there a train in here? Someone want to interpret the intercept? Yeah, Claire. Okay, so if you don't sleep at all, you get a 42. This is not going to happen very often. Like, this is almost certainly outside of our sample. Like, we don't really see any data here. But this is how we would interpret it. What about this one? So let's interpret the slope.
Wouldn't that be for every hour's sleep, the student gets 5%, 5.8% better on the exam?
Okay, so if the test score was as a percentage, which I think it is, then we would say every 1 unit increase in the predictor variable increases the outcome by 5.8, which I would also interpret this as percentages. Yeah, so every extra hour, does this feel right? Maybe a little bit low, I don't know. Yeah, so nice, really nice. This is how I wrote it in the slides. Any question about this? Is that a complete sentence? Any question? Only one. What about this one? What's the null hypothesis for the slope coefficient? We'll take about a minute here, or 30 seconds. Maybe check it with someone. Okay, null hypothesis. Someone want to tell me what it is? Matt.
Null hypothesis be that the number of hours sleep doesn't impact the test score.
That's right. The null hypothesis is that the slope is 0. So in this case, that would say if the slope was 0, it would be no relationship between hours of sleep and test scores. Okay. Any questions here? This is our default null. Whenever we run software, this is what it's checking. And then what about this one? What test score would the model predict for a student who sleeps 8 hours? Take about a minute here. Just a second. Okay, someone want to tell me your process? Like, how would you go about answering this? Brad.
I just kind of did it like an algebra problem. So you take 42.3, that's the baseline,
Okay.
and then you multiply 5.8 by 8, and then you add 2 up, and you get 88.7.
Okay, so we have an equation. We know what beta 0 is because we estimated our model. We know what beta 1 is because we estimated our model. And we're saying we're going to try to make a prediction using this linear model at an x value of 8. So all we do is we plug in 8 using the coefficients for mx, for m and for b in our mx plus b. And what was the number we got?
Oh, yeah, well, I literally just did like what that says right there.
This thing.
Yeah.
Yeah, nice. And you got 88.7?
Yeah, I just typed it.
Nice. So calculator problem. You probably did this in high school. Any questions here? The thing you did in high school allows you to make predictions using statistical models. The equations we run, the statistical models we run, like 90 to 95% of the time are no more complicated than a linear model like this. Usually they have more terms, but it's just like this. All right. Y'all ready for question 4? We're going to try to draw the sampling distribution. So we're going from simple to complicated, or from simple to more complicated. This is 4 out of 7. So here we're drawing the sampling distribution of beta 1 under the null hypothesis. We'll take maybe a minute here. Check your answer with someone next to you. This question will be on the mini exam. Okay, someone want to give me a picture, like describe a picture, and I'll draw it on the board? What's the sampling distribution of beta 1 under the null hypothesis? Yeah, Pete.
I started off by drawing like a normal distribution almost.
Okay.
So there's sort of like the normal distribution curve that would look like.
Yeah.
And then if it's under the null hypothesis, it would be centered on 0.
Okay. So our null hypothesis is 0. We're saying the sampling distribution is the sample of our data, the sample slopes drawn from that assumption of there being no relationship between the variables. So we're going to center our sampling distribution on 0, which is our null hypothesis.
And then beta 1 is equal to 0.75.
Okay.
So I just put that on either side. So like, plus and minus.
Yeah,
on either
plus and
side
minus.
of the distribution.
So Pete's going one step further, which we'll get to in just a second. Okay. I'll put that on the board in just a second once we get there. Any questions about this? So this is a nice picture. This has lots of other things, but the sampling distribution under the null hypothesis is going to look like this. This is our this is the distribution of beta 1s. Any questions here? This is like what we spent most of part 3 doing, and then extended into slope parameters in part 4. Okay, so maybe I'll just draw all of this up, and then we'll talk about it. Looks like I don't have separate questions for the second parts. So what Pete is saying is what we observe is 1.5. So our observed beta 1 is 1.5. So then we would want to find the entire area more extreme than this to get our p-value. We also have, the negative of that. So negative 1 beta would be negative 1.5. So this is everything that's equally as extreme, but on the other side. Okay, so we have our sample, we have our null hypothesis, we have our sampling distribution, and we have our p-values. So the way I would set this up, I'm just going to give you like 4 or 5 different steps here, just thinking about the null distribution. The first thing to do, we know from the central limit theorem, the sampling distribution will be a approximately normal distribution. That's what the central limit theorem tells us. We use the default null hypothesis of no relationship of 0. So this sampling distribution under the null hypothesis will be centered at 0. The second step would just be to label the x-axis. So I'm just saying this is what the distribution is over, and then we're centering it on 0. And then one of the last steps is just to mark the sample slope that we actually observe. So we don't see everything else. All we see is just this one thing. Then the probability of seeing that thing or something equally as extreme is how we define the p-value. That p-value is just the area under the tail more extreme than what we're seeing. So everything that's further away from our null hypothesis than what we see. This is the p-value, which gives us some indication of the sort of consistency of our sample with a null hypothesis. Any questions about this? Yeah. Okay. Here.
Yeah. It says mark 0, the null is null.
Oh, doesn't matter. Just mark it. Doesn't really. Yeah, Mairead?
Also in your model, you're doing beta 1 is 1.5. Is 1.5 the 0.75 added up twice?
Oh, I'm sorry. That should be 0.75. That's my mistake. 0.75. I can't read and everyone gets a heart attack. Okay. Any questions here? Any other mistakes I made? Yeah.
So I just have one question. Are we supposed to draw the p-value into our graphs, or
I would probably ask if I really needed it. I would ask for it. In this case, my question is a little underspecified here, but I think on mini exam 3, I asked for you to do something like this for the means, for the intercept coefficients, and I asked you to graph in the p-value on a figure. So yeah, sometimes I would ask for that. Any questions here? This is one of the biggest ideas we have. Like, this is how we go from a sample to something we can make claims about. Okay, number 5. So let's say we have a binary predictor. So I have GPA data on 100 students. This is all fictional. And I'm looking at on-campus versus off-campus. And then I have some GPAs. We love students on campus and off campus. I sort of don't love this question. But this is data we could collect. So first question, if we code on campus as 1 for yes and 0 for no, what is beta 0 representing? So we'll take maybe 30 seconds here. This is similar to questions we've covered before. Okay, someone want to tell me what beta 0 is representing in this case?
Should be the age of year for people off campus.
Nice. So we're coding off campus as 0. So the intercept term at 0 is the average for the 0 group. Yeah, nice. Any questions here? What about beta 1? Take maybe 30 seconds. And maybe try to communicate this in English. That's a question I will ask for. All right, someone want to tell me? What does beta 1 represent? Yeah, Matt.
The increase in GPA on-campus students.
So yeah, the difference in GPA between on-campus and off-campus. I can't write down 0.5, 0.75, and I also tossed my marker apparently. So yeah, that would be the difference. And if we knew the number, we could say this directly in English. We don't have numbers here, so we just say it with beta 1. Any questions? Okay. We've asked this kind of thing before, so maybe we'll skip that. Let's go to, I think we have 2 more questions, 6 and 7. Here I have 3 residual plots. So we have the predicted values on the horizontal axis, and then the residuals, so the difference between the predicted value and the actual value on the vertical axis. So I gave you an answer on screen accidentally. So we're going to go through each of these 3 and sort of check which model assumptions are violated. So let's spend maybe a minute or 2 here thinking through which of the assumptions each one of these patterns is violated. Okay. What about pattern 1? Sorry. What about pattern A? Yeah, but linearity. And why is it linearity? Yeah, nice. Also, I gave the answer on screen. Okay, so yeah, linearity. This is U-shaped, and like we talked about like 2 classes ago, the data itself gets sort of reformatted into the error terms. So if the residuals are not linear, then this violates the assumption of linearity. What about pattern B? I didn't give you this one. Pete? Homoscedasticity. So this is an example of heteroscedasticity, where we have differences in the variability of the error terms. So for small predicted values, there's not a lot of variability, but for large predicted values, there is a lot of variability. Okay, and what about for pattern C? This looks good to me. I'd say probably none of the assumptions are violated here, at least none that we can see. Any questions here? Isaias? Yeah, so why is this a problem? Yeah, so the short answer is like the way we do the math behind the scenes requires the error terms to be consistent across the predicted values for the p-values to be correct. That's the short answer. Yeah, the long answer requires, I think, a little more complicated math than what we're doing in this class. But it's sort of like if we use the standard error, like the variability in our data, to tell us about the size of the sampling distribution. And if there's sort of variability in the standard error, which comes from the size of the distribution of the error terms, then that shape is kind of wrong. That's the short answer. Yeah, nice. Any other questions? Okay, so here I have lagged residual plots. Which of these plots shows autocorrelation? We'll take maybe a minute here. And when you're thinking about answering this, think about kind of why each one is showing autocorrelation or not showing autocorrelation. Like what's the reason for it? Okay, someone want to help me out here? Hands up if you think Model A shows autocorrelation. Hands up if you think Model B shows autocorrelation. And everyone else abstains. Except for Mairead. Model A shows autocorrelation. Someone want to tell me why it's Model A? Because A stands for autocorrelation. No. The horizontal axis represents the residual in the previous period. So we're just like one row before. And then the vertical axis represents the residual in the current period. So in the row we're looking at. So we're just looking at the error term, like how wrong the model is in two adjacent rows. And we're checking whether those two errors are related to each other. When we have autocorrelation, relationships between our error terms, the two values will be related to each other. So we would see one error being related to the one before it. And that would give us a positive relationship. So when one is negative, the other will be negative. When one is positive, the other will be positive. So we would see this. If there was no relationship, it would look something like this, like Model B. Any questions here? All right. So I think that's the end of my guide here. So the core skills here are just thinking about data. We've done a lot with data visualization. The key trick is just realizing our core statistical models are just drawing lines through data. And in the general linear model, these lines are all linear for the most part. We interpret beta 0 as the predicted y variable when the x variable is 0, whether that's in binary predictor world or whether that's in numerical predictor world, where we have some x that takes on a number. Either way, we interpret beta 0 the same way. Beta 1 is just the change with 1 unit on the horizontal axis. So how does y change when we move by 1 on the horizontal axis? That's the same whether we're thinking about numerical predictor variables or binary categorical predictors. We think about the sampling distribution. It's a bell curve or an approximately normal distribution like this, coming from the central limit theorem. We don't see all of the samples that we could draw. We only see one. So our question is generally, when the bell curve is centered on the null, what's the probability that we see something as extreme as what we do? And that gives us the area in the tails. We interpret that as the p-value, which is the probability of seeing a slope as extreme as ours if the true underlying relationship were 0. These are fundamentally the same ideas as part 3, just applied to slopes. All right, so these are the core skills. And then, yeah, thinking about residuals, and then so residual plots and lag plots to check our model assumptions. Any questions about any of this? All right, so we have 15 minutes left in class. If you want to stick around and ask questions about any of this, that's what I'm here for. I want to set you loose on your Part 4 projects. This is really a good time to get started thinking about the question you're trying to answer. You've already given me lots of evidence of work with your own data sets from the Part 1 project and the Part 2 project. This probably feels like it was a while ago. What you're going to do for me is give me a couple of extra things in the Part 4 project. Here, in addition to working on data visualizations, which we've done, you're going to start developing a statistical model to test relationships between variables. We've already done a lot of the work, right? The Part 2 project, you've already shown me that you can relate two variables together. What you're doing in the Part 4 project is testing that slope. That's the core contribution of Part 4. So if you go to the guidelines, oh, this is not posted. Let me show you, I'm going to post this right after class. Let me just show you what that looks like. So what I'm looking for from you is for you to build a statistical model using the concepts in Part 4. So the first thing is just, I want to know formally this time who your group members are. So just, I have an entry box, just tell me who you're working with. If you want to work by yourself, I discourage it, but I allow it. You just have to come talk to me. So make sure that we've talked about this before you submit. This can be over email, so if you really want to work by yourself, just either come chat with me right now or send me an email and I can make that happen for you. But I just need to sign off on that. Then I need an equation for your model. So we've done a lot of this, right? Like building equations for lines through our data. This is your chance to do this for the data set that you've been working with. And then this is not going to be that much more challenging than what you did in Part 2. Essentially, you've already done this in the Part 2 project. So so this should already basically be set up for you. If you wanted to add a line of best fit, you could do that here as well. And then you're going to fit the model and then show me the summary. So you're going to give me a model output. And then the last thing is for you to interpret the betas and the p-values in English. So you'll put all of this in a text document for yourself. Keep track of this. This is going to go into the final project. We're going to do something similar in Part 5, so keep this in mind. These are all going to give you essentially a starting place for your draft for the final project, which is going to be 1 to 2 pages. So keep that in mind. This is going to be short. Most of the work we're doing is building the statistical models, running them with data. So take a look at this document. Looks like I need to post it, but these are the main things to keep in mind for the project. This is on Gradescope, so you can take a look at that. We have like 15 minutes in class, so this is a good chance to chat with your classmates, or if you want to chat with me, I'll be here.